Okay, good. Oh, there I am. I wanted you to have something to read when I was being introduced, but now it's up anyway. It's a real pleasure to be here, even if it is too early in the morning for me and for you. But this will just be entertainment, so it's okay. You can sleep and then you can wake up for the other talks. It's okay. It is also... my mother, who is 97 years old now, just happened to tell me before I was coming here that her mother, who I always thought was born in Poland, was actually born in Ukraine. So it's nice to be home, again, in a way. Yeah, okay. Good. Okay, we've begun late anyway, so I've tried to reduce what I say because I'd like to be able to answer some questions. But what I want to talk today, and since space is the theme, I will be mostly talking about space, but I want to make connections between what I'm doing and let's see, the problem with putting something in and not after you've tested it is when you take another computer, it doesn't work very well, so I'll have to do this. Okay, we'll see if we can get that. I want to relate, it's nice to be around people who are doing something useful, because I don't. My own field is I'm very proud of the fact that nothing I've ever done has any practical significance whatsoever. But there is a relationship between the work people like me do and the work that people like you do. And I'm going to try and see if I can fix this, because I'd rather be able to have my pointer work. Oh, good. Okay. Many years ago, I was chairman of a physics department, and I created a new program, and the program was called Physics Entrepreneurship. And the dean of our business school thought that was an oxymoron. Now, maybe you don't know what that word is. It means two words that should not go together, physics and entrepreneurship. But in fact, scientists are entrepreneurs. And the same tools that you use when you're developing new codes, new products, new ideas are the same things that we use in discovery. And that's what I want to talk about today, in a sense, with some examples from the real universe. So the tools of discovery and the tools of entrepreneurship are very similar. And one of the first things we discovered when I created this new program, we went out to physicists who had developed companies, and we said, what didn't we teach you that you could learn effectively, and that we should teach students who want to create new products and new companies? And the first thing was how to fail productively. We make the mistake in school of giving people problems that they can always solve, but in the real world, the problems often cannot be solved. And often you find yourself solving a problem that wasn't the problem you thought you were developing. Sometimes when you're making code, the end result is something very different from what you started. So the thing to remember is that it's okay that if you move away from where you started to go from, it actually might even be better. And I'll try and show you some examples of people trying to solve one thing and what they ended up with was much, much better from our study of the universe. You heard people, those of you who are going to confess into that booth, you don't really have to confess, because the mistakes you make are essential for making progress. If you're not making mistakes, you're not making progress. View every accident as an opportunity. This, of course, is my guide. Often, let nature be your guide, because the key thing that I want to try and emphasize, and I always do when I'm talking about the universe, the reason I enjoy being a scientist is that the imagination of nature far exceeds the human imagination. I'm a theoretical physicist, and if you lock theoretical physicists in a room without windows, and asked them to develop a theory of the world, it would be far more boring than the real world, because every day we're surprised. And I often say, every day when I wake up, I'm surprised if I'm not surprised, because the universe is stranger than we could have imagined. Looking outside the box is the other aspect that's probably very important for you, but it's very important for science, and I'll give you a specific example in a moment. Never ever give up is the other thing I tell my students, because good things are hard and they take a long time, and it's very easy to think that you're not making progress. When I was much younger, actually before I spent most of my time in front of a computer, I'm old enough that I remember when I used to work on pieces of paper. And my daughter, when she was 4, was asked what her father did at work, and she said, he stares at a piece of paper, because that's what I did. And most of the time I would not make progress, and every now and then I would. And the last thing I want to talk about, if you can see down here, is different is not bad. What looks good changes with time. In fact, as I'm saying this, I remember talking to someone who was a very well-known scientist. I bought the very first, I was at Harvard University, and I remember buying the very first Macintosh computer when it first came out in 1984. And a friend of mine, he was a computer expert. He actually wrote a very famous book on programming. But he said, this mouse, no one will ever want to use a mouse. No one will ever want to use the mouse, because at that time, he said, it will never catch on, so it won't be popular. And he was an idiot. Okay, so those are the ideas, and I want to point out also that too often people get hung up on making applications for something specific. But curiosity-driven research is vitally important, because the work we do at the forefront, driven just by curiosity, will eventually become applications that change the world. And 50% of the current United States gross national product comes from curiosity-driven research a generation earlier. And I want to just begin by pointing out, if we were driven by applications alone, this is the famous Babbage analytical engine. Babbage, who first developed the idea of a computer. If in the 1940s and 50s in Bell Labs, if people were trying to develop a better computer, a faster computer, they would have developed new cogs and new wheels, and that's what we'd have now. But instead, the scientists at Bell Laboratories developed this device here, which doesn't look like much, but this is the very first transistor that Bardeen, Shockley, and Britton created at Bell Labs. They won the Nobel Prize for it. And of course, it changed the world, because computers then became driven by these switches. But it's certainly not what would have been developed if people were just trying to develop a faster computer at the time. In my own field, and I may well talk about it at some point today, this is the Large Hadron Collider in CERN in Switzerland. If you go to the airport in Geneva and land and you look out at the countryside, underneath the countryside is one of the largest tunnels in the world, the Large Hadron Collider, which crosses France and Switzerland. And we send particles around at 99.9999999% the speed of light in this direction and this direction, and we collide them in several places to try and understand the fundamental forces of nature. Nothing could be more esoteric than this. But because it took, to build this machine and operate these experiments, it took over 10,000 PhD physicists. 10,000 from many different countries, from over 100 different countries, speaking many different languages in many different locations, to develop these large machines and experiments required a whole new way of working, beginning in the 1980s. And what had to be developed was a way for scientists to communicate to each other across the world on a common problem without worrying about which machine they were on. So what did they develop? The World Wide Web. The thing that employs all of you today was developed because of the need of particle physicists to be able to communicate with each other on a very esoteric problem. We never know where the next technology for the future will come from, but probably it will be driven by research at the forefront. Okay, now let's get to some science. This is a galaxy. It's not our galaxy. Why? It's early in the morning. I want to make sure. We live in our galaxy. Most of us live in our galaxy. In my country, the president certainly doesn't live in our galaxy, but okay. Yeah, anyway. This is the Andromeda Galaxy, the nearest large galaxy to our own. It's a spiral galaxy, much like ours. And until 1989, we really never had a picture of our galaxy, because most of our galaxy is obscured by dusk. We live at the edge of the Milky Way galaxy. If this was the Milky Way, we'd live around here. And you can't see most of the galaxy because it's obscured by dust. But we can look up and see other galaxies. But in 1989, we sent a satellite up above the Earth's atmosphere to look at radio waves and microwaves, which can go through that dust. And for the very first time, we got an image of our galaxy. This is from the Kobe satellite. This was 1992. This is our galaxy as seen from where we are at the very edge. And you can see it's a spiral galaxy. We always told people that in school, but we'd never had a picture of it. They made a better picture later to superimpose the stars on top of it. But this is our home galaxy. Indeed, it's a spiral galaxy. Now, as we tried to, talking about accidents and thinking about accidents, I want to begin by talking about this man here who was a hero of mine. His name is Edwin Hubble. This is Edwin Hubble with the Mount Wilson telescope in 1925. Actually, it's probably about 1929 because he became famous then. But in 1925, my mother was born before 1925. The entire universe consisted of one galaxy. For scientists, our Milky Way galaxy was the universe, less than one human lifetime ago. And with the Mount Wilson telescope, he looked out and was able to see for the first time that these fuzzy things, that was called nebulae, which is Latin for fuzzy thing, were not just stars in our galaxy, but were other island universes. And he began to suddenly realize that there were other galaxies in the universe. A single human lifetime ago, he realized that. We now know that there are over 100 billion galaxies in the universe. And 90 years ago, we knew of one of them. So that's how much things have changed, in a sense. But I want to go back further. This is a picture I took in Sweden many years ago. It's an island off Sweden, the island of Ven. It used to be an island off Denmark, but Sweden was an imperialist country and took over this island. This island, on this island, there's a statue of this man here named Tycho Brahe. And he was the first person to basically, before the telescope was ever invented, he spent his entire life measuring the position of planets on the sky every night. That's all he did. And I don't know why he did it, but he did it, and he did it better than anyone had ever done before, which is quite amazing because the Babylonians, the Chinese astronomers and astrologers at the time had measured things carefully, but he improved our ability to know the position of the planets on the sky by a factor of 10, night in, night out. And then he was a feudal lord. He actually owned this island because he discovered what we now know is an exploding star, which I'll talk about later. And the emperor of Denmark gave him this island when he discovered this supernova, and he made him a feudal lord. And he had the whole island. He was a very bad feudal lord. He had a pet dwarf who he put on a chain, and also a pet reindeer. And after 20 years, the emperor changed, and the people on the island didn't want him anymore, and he got kicked off, and he went to Warsaw, actually. And there he found an assistant, a young man, and he did what we professors always do with our assistants. He gave him the 20 years of data, and he said, figure it out. And the young man was named Johannes Kepler. And Johannes Kepler spent almost 20 years analyzing that data without a computer, without Java. And he discovered something remarkable, something unexpected. And I took this from a first-year astronomy textbook, but he discovered there's a relationship between the speed of the planets around the sun and their distance from the sun. It's a remarkable relationship. It's that the speed of the planets from the sun falls off as 1 over the square root of the distance from the sun. That was basically what Kepler discovered. And that discovery made Isaac Newton rich and famous. Because Isaac Newton, so he discovered that there's this mathematical relationship between the speed of planets around the sun and their distance from the sun. Now what Isaac Newton realized is, he realized that if there's a force of gravity, and the force of gravity has this form, and you all remember it from your, either fondly or not so fondly, from your high school physics class, which all of you took, I assume, because you really can't be a good developer unless you took physics at some point in your life. If you assume this force is there, then he could make a prediction. The prediction he made was that the velocity squared of planets would fall off in the distance with the sun. This is the prediction. But this allows us to do more. Because if you measure the velocity and you measure the distance, then you can measure this thing. And this is the strength of gravity. This is the mass of the sun. So what's realized is that you can use that curve from Kepler to measure the mass of the sun. You can weigh the sun just by measuring the speed of planets around the sun. And that's exactly what we do here. This curve is so good, it fits the data so well, that in principle you could measure the mass of the sun to 1 part in a million with this data. You can't quite do that because in fact we don't know the strength of gravity to an accuracy of 1 part in a million, because gravity is the weakest force in nature. And so this is the limiting factor in measuring the mass of the sun. But this tells us the mass of the sun is this number. Great. So we can measure the speed of objects a certain distance around the sun, and we can determine the mass of the sun. So, like Hollywood, and probably like software development, there's a famous algorithm, and that is, if it works, copy it. Okay, we see it all the time in everything that's done, and certainly in Hollywood, I think there's Halloween 18 just came out, and there's all sorts of, every movie is done 10 times until it stops making money. And so if it works for the sun, let's make it work for the galaxy. Remember, this is the Andromeda galaxy, but it could be our own, and our sun is over the edge of our galaxy, going around our galaxy. It goes around our galaxy once every 200 million years at a speed we can measure. And if we know the distance from the center of the galaxy and the speed it's going around, we can weigh our galaxy because we're right at the edge. Now, how do we determine our speed in our galaxy? Well, we have to use physics, of course, and these two cowboys watching this train on the plain, probably in Arizona, know how to do it, because one says to the other, I love hearing that lonesome wail of the train whistle as the magnitude of the frequency of the wave changes due to the Doppler effect. And as you know, when a train whistle comes towards you, it sounds higher. When it goes away from you, it sounds lower. Same for an ambulance or anything. That's a Doppler effect. Waves get compressed in front of an object that's moving and stretched out behind an object. The same thing happens for light. So if we look at a star, it emits light of a certain frequency, generally the frequency that hydrogen, because stars are made of hydrogen. When you heat hydrogen up in the laboratory, it shines with a certain set of frequencies. If the star is moving away from us, the light gets stretched out to longer wavelengths, and longer wavelengths are the red part of the spectrum. If it's moving towards us, it gets scrunched up to the blue end of the spectrum. If we're looking at a galaxy that's rotating, the stars that are moving towards us will be shifted in one direction. The light from them will be shifted in one direction compared to these stars, and we can measure the speed of rotation of our galaxy, of any galaxy, including the speed of objects in our galaxy. So that's how we can measure the rotation rate of galaxies. So here's our galaxy once again, and in the 1970s, Vera Rubin, who should have won a Nobel Prize but didn't, she's died now, she began to measure the speed of objects in our galaxy in order to try and determine the mass of the galaxy. Now, I told you we know the speed of the sun. The sun is about 30,000 light years from the center of the galaxy, or 8 kiloparsecs in language that we use in astronomy. And it's moving at 220 kilometers per second around the galaxy. 200 million years to go around the galaxy. But this single data point, since we're at the edge of our galaxy, once we know the velocity, and once we know the distance, v squared equals gm over r, we can measure the mass of our galaxy contained inside our orbit. And we do that, we find from this single spot that the mass of our galaxy is 100 billion times the mass of our sun. And when we do that, we jump up and down with excitement, because if you count the number of stars in our galaxy, it's roughly 100 billion stars, so everything works. But of course, and this is what Vera Rubin wanted to do, we could do what we do for our sun. We could try and measure the speed of objects further away from the center of our galaxy than our sun to try and fit this curve better. But because we're at the edge of our galaxy, there should be nothing out here, so this should fall off as 1 over the square root of r. And she started to do that in the 1970s, and other people started to do that in the 1980s. And what we discovered was it doesn't work. Now, this is the point. Every accident is an opportunity. Every mistake makes progress. This is the worst possible fit you could imagine to this curve. If you produced it in an undergraduate physics class, you'd fail. But this is the way the world really works. So how can you understand this? Well, since v squared goes like gm over r, v is constant. Here are globular clusters, the Large Magellanic Clouds, satellite galaxies out to 10 times as far away from the center of the galaxy as we are, and their velocity remains constant. How could you understand that? Well, there are 2 possibilities. First, gravity may break down, but who would expect that? The other possibility is, if v squared goes like gm over r, if the mass of our galaxy increases linearly with the radius, then mass goes like radius, mass over radius become a constant. So the way to understand this is to say that the mass of our galaxy is growing, continues to grow as you go further and further away from the center of the galaxy. There's more and more material, but we're at the edge of our galaxy. All the stuff that shines is inside this region. What does this mean? It means that 90% of the mass of our galaxy is invisible. It doesn't shine. And physicists, because they're not very creative, at least with language, call this dark matter. And what was discovered was most of our galaxy is invisible, and it's dominated by some material that doesn't shine like stars or hot gas. Now, the first time you see something like this, you should be very suspicious, because almost the first time anything is measured in science, we get it wrong, especially in astronomy. So the idea is to look at other galaxies, and every galaxy we can measure, if we measure the rotation curve, if the mass was where the light is, the curve should fall off like that. These are many different galaxies. The curve always remains constant. Every galaxy we can see is dominated by dark matter. What we've discovered is that most of the mass of the universe, 90% of the matter in the universe, doesn't shine like stars. And in fact, that mistake changed everything. Because we now know, for reasons I don't have time to go into here, that there isn't enough matter made of the same stuff as you and I, protons and neutrons. There's not enough matter in the universe to account for this by a factor of 10 almost. We now think that this dark matter is some new type of elementary particle, different than anything we could measure on Earth here in this room. And this dark matter is responsible for why we're here. Galaxies wouldn't form if this new type of matter wasn't there. There wasn't enough time in the history of the universe for galaxies to collapse if this dark matter wasn't there, we think. But it's even more exciting because it means the dark matter isn't just out there. If it's made of elementary particles, then it's in this room. It's going right through your bodies as you fall asleep during this lecture. And it means we can do experiments here on Earth to look for it. So this accident of trying to weigh our galaxy suddenly caused us to discover something much more interesting. If the galaxy had been exactly as we expected, big deal. Who cares what the mass of our galaxy is? We'd have a better number. But by making a mistake, we discovered a whole new part of the universe. Not just a new part of the universe, but the most important part of the universe. So that's the other thing you should get out of this talk, is that you are far more insignificant than you thought. Okay, that's really important. Applaud, yeah. Because we are just a bit of pollution in a sea of dark matter. We are irrelevant to the universe. So there are many people, maybe people in this room, who somehow think the universe was created for us. No. We're irrelevant. We could be gone, and everything we see, all the stars in the night sky, everything we see in the universe could disappear, and the universe would be essentially the same. But this is a nice story. But science isn't based on stories. If this dark matter is made of a new elementary particle, we should be able to look for it. We should be able to detect it. And for example, here's one of many kinds of detectors that are being built underground to look for this. Because why underground? Because we think this dark matter interacts so weakly that it goes most of the time right through the Earth. And as we stand here, we are being bombarded by cosmic rays. And if you put a detector on the surface of the Earth, it would be bombarded by cosmic rays, and it would never detect dark matter. But if you put it in a deep mine underground, the cosmic rays get shielded. This is, you should all be familiar with this because this is silicon or germanium, the basis of computers. And if you cool silicon or germanium down to 1/1000th of a degree above absolute zero, a little bit colder than it is today here in Kyiv, but not much. If you cool it down to almost absolute zero, most of the dark matter will be coming right through this. Billions and billions of particles every day going through this, but we can estimate that maybe once every day, or maybe once every year, a dark matter particle will bounce off an atom of silicon or germanium, deposit a little bit of energy, and heat the whole thing up by 1/1000th of a degree. And we propose these detectors. Actually, I proposed them 35 years ago almost, and now they're being built in mines in Europe, in the United States, now in China. Detectors like this looking for this matter to discover perhaps what it is that makes up most of the mass of the universe. But what makes it really exciting is that there's a race. Because we may be looking, these dark matter particles were created at the beginning of the universe. But there may be another place to create dark matter particles. And that's here. This is the Large Hadron Collider. A superconducting collider. As I say, it's 26 kilometers around in Geneva. It is the most complicated machine ever built by humans. The detectors alone to detect the collisions of what happens here are themselves unbelievably complicated. This is one detector, the Atlas detector. This is the compact muon solenoid, the smaller detector. There's more metal in this detector than there is in the Eiffel Tower. The magnetic field is so great that there are two halves of this detector. I have a better picture because I'm in it. But there's one half here, there's another half here. They come together. This is when it's being worked on. But the magnetic field is so great that even though they're not on rollers, and even though each weighs many tons, if the magnetic field was turned on, those two pieces of detectors would come together. Incredibly complicated, but the idea is if we can recreate the conditions of the universe in the first millionth of a second, maybe we can create the particles in the laboratory that were created at the beginning of time. And so there's a race to see whether we can create the dark matter particles first at Geneva or first underground. But building this detector itself and these detectors produce technological challenges, not just the creation of the World Wide Web, but new programming challenges. Every second at the Large Hadron Collider, enough data is generated to fill more than 1,000 1-terabyte hard drives. So you can imagine the programming challenge to be able to manipulate and store that kind of data. In fact, most of it you have to throw out. Whole new kinds of parallel computing and programming had to be developed to be able to understand this. So again, it's an opportunity at the forefront of science to develop new ways to deal with data. Now, there's another accident that come from Hubble. When Hubble looked around and discovered that there were other galaxies, he was also able to use the Doppler shift to see something. And what he discovered is something remarkable. These are not sperm, by the way. These are galaxies, just in case you're wondering. This is not a biology meeting. This is our galaxy, and what he discovered was absolutely unexpected. And for a long time, people didn't believe it, even Hubble. On average, most of the galaxies in the universe are moving away from us. Those that are twice as far away are moving twice as fast. Those that are 3 times as far away are moving 3 times as fast. We codify this in a Hubble's law. The velocity is proportional to distance, and there's some number here that we spent 100 years trying to measure. But what happens when you look at that? What does it tell you? It tells you that we are the center of the universe, right? Obviously. Well, for some of you, you are the center of the universe, but it's not the case. And here you have to think outside the box. When you see data like this, the first thing tells you, you are the center. We all make the mistake of assuming we are more significant than we think we are. But to really see what's happening, you have to get outside the box. Now, it's really hard to get outside our universe in real life, but I can do it on the board really easily. I can make a 2-dimensional universe. Let me put a 2-dimensional universe with all the galaxies at nice uniform distances apart from each other at time 1. And then if the whole universe expands a little bit, then that region gets a little bit bigger at time 2. So if we were standing outside the universe and seeing it was expanding, this is what we'd see. At time 1, that region would look like this. At time 2, it would look like this. But now let's ask ourselves, what would it look like if we were on one of these galaxies, say the Milky Way? Well, we just have to superimpose this image on top of this image, placing the Milky Way on top of itself. And what do we see? Everything's moving away from us. And it doesn't matter what galaxy you pick. Every galaxy you pick, you see the same thing. Every galaxy, computer Java programmers on that galaxy are thinking that they're the center of the universe. And on this galaxy, and this galaxy, but what we've discovered is not that we're the center of the universe, but that the universe is expanding uniformly. Again, it's hard to imagine how much things have changed. In 1925, there was one galaxy in the universe that we knew of, and the universe was static and eternal and empty, except for our galaxy. But now we know the universe is expanding, and that means our universe had a beginning, the Big Bang. If we work this picture backwards, 13.8 billion years ago, our entire universe began in an incredible, massive explosion. And that itself is interesting. to try and understand the beginning of the universe. I spend most of my professional career trying to understand that. I've written books about it. But the obvious question is, if it's expanding, will that expansion stop? And the reason I got into cosmology as a young scientist was to be the first person to know how our universe would end. Would it end with it collapsing in the reverse of the Big Bang, or would everything just expand forever? Would it end with a bang or a whimper? And I thought, well, I thought that was a good reason to get into the field at the time. It turns out it wasn't a good reason, but in any case, to know the answer, we have to know how much matter there is in the universe, because matter attracts, and so if there's lots of mass, the gravitational attraction will slow down the expansion of the universe. And so that's why we wanted to know how much dark matter there was, because if there's enough dark matter, maybe it would stop the expansion of the universe and cause it to collapse. That's why I got interested in dark matter. It turns out, due to Einstein, gravity is really a reflection of the curvature of space, and I can't draw curved three-dimensional universes, but I can draw curved two-dimensional universes. This is a closed universe, an open universe, and a flat universe. What really matters is to determine the geometry of the universe, and the geometry of the universe is determined by how much matter there is. And if there's enough matter, then the universe will expand, stop, and recollapse. If there's not enough matter, it'll go on expanding at a finite rate forever. If there's just the right amount of matter, called a flat universe, then the universe will expand and slow down and never quite stop. It will asymptotically approach a static universe. And if we could determine which universe we live in, we'd know the future. And that was my goal as a scientist. Now, to do that, we have to weigh the universe. We weighed the sun, galaxies, etc. And here is, by the way, Hubble's data from 1929. This is velocity as a function of distance. This is why he was such a great scientist. He knew to draw a straight line through this data set. It's not at all clear that if you did any of your algorithms that you'd come up with a straight line here, but he guessed, and he was right, except he got the answer wrong by a factor of 10. That's okay in astronomy. It turned out to be a little embarrassing because he got that the expansion rate of the universe was 10 times faster than it actually is. And if the universe is expanding 10 times faster than it is, then it turns out the age of the universe is 10 times shorter than we thought. And if this were true, the universe would be less than 1.5 billion years old. But already in 1929, we knew that the Earth was older than 1.5 billion years old. Well, we knew it except in Arkansas and Tennessee and other places in my country. But in the civilized world, we know that it's older than 1.5 billion years old, and it was embarrassing to find the Earth being older than the universe. Had that been the case, that would have been fascinating, but happily, it turns out it's not true. The expansion rate is much smaller, and the universe is almost 15 billion years old. But the idea is, if we could, these are fairly close by, these are the nearest galaxies. But if we could measure the expansion rate of the universe over time, we could see whether it's slowing down and how quickly it's slowing down, and then we'd know what the end of the universe would be like, we thought, how much dark matter there is. And so the idea was to say, well, let's measure the expansion rate of the universe, not for nearby galaxies, but for galaxies billions of light years away, and see how fast they're moving, and seeing how fast the universe is slowing down. We knew it had to be slowing down because gravity is attractive. So astronomers started to look for objects that could allow us to measure the distance to very far away galaxies and measure their speeds. And here's one such object. This is a galaxy, long, long ago, far, far away. Not that long ago and not that far away. This is 75 million light years away. That means the light from this galaxy took 75 million years to get to us, to have this picture taken. But 75 million light years is not that far in a cosmic sense. But notice this object here, which is shining with the brightness, the same brightness as the entire center of that galaxy, containing 10 billion stars. What is this object? It's a star that's just exploded. And It's a supernova. The same thing that Tycho Brahe saw when he measured an exploding star 400 years ago. But these objects we now understand are wonderful standard candles. We know how bright they are, the fundamental physics of them, and therefore if we can measure and see how bright they are in our telescopes, we can determine accurately how far away these objects are. The problem is stars only explode once per 100 years per galaxy. So how can you measure exploding stars? Well, the simple thing is you assign a graduate student to each galaxy. 100 years is about the right time for a PhD. And if graduate students die, it's okay because they're cheap. You can just get a new one. Some of them get discouraged and go in to become programmers during that time where they can actually make some money. But anyway, we don't have to do that because the universe is big and old. And rare events happen all the time. And if you take a small hole about that big and hold it up to the night sky in the countryside, if you have a telescope as big as the largest telescopes we have in Chile right now, say, you will see in that little region that big in the sky over 100,000 galaxies. And if you work it out, if stars explode once every 100 years per galaxy, then on a given night you'll maybe see 3 or 4 stars explode. And astronomers do that. They look and they measure stars exploding. Here's a region, here's a star, and they get bright. This will repeat. An exploding star gets bright for about a month and gets certain colors. And because of all this, we can know about the nature of that star. We know how bright it is. We can determine how far away that galaxy is. And in 2000, over the period about 2005 to 2008, even before that, people started to use these supernovae to try and measure the rate at which the universe is slowing down, so they could see how much dark matter there is and how our universe would end. And what they discovered was something utterly shocking. They made a huge error in their assumptions. Here is the Hubble curve, velocity versus distance, on a logarithmic plot where everything is a straight line. And the idea is to see how much this curve is bending down. So to see that, I'll just draw a straight line through that curve. And the idea was to measure all these distant supernovae were supposed to fall along this curve because our universe is slowing down. But what was discovered was something quite different, totally unexpected. All these supernovae lay above the straight line. What would that mean? Well, the only way to understand that is if our universe is expanding ever faster with time, not slower. Our universe is dominated by some kind of cosmic anti-gravity. What could cause that to happen? Only one thing. If you put energy into empty space, it's gravitationally repulsive, not attractive. Gravity blows, it doesn't suck. If you put it in empty space. What does that mean? If I take a region of space and get rid of all the particles and all the matter and everything that's there, if it weighs something, if empty space weighs something, you could understand this. But that's crazy. Why would empty space weigh something? The answer is we don't know. It's the biggest mystery in science right now. But in fact, we now know that almost 99% of the energy of the universe resides not in matter, but in empty space. So now you're even more insignificant than you thought you were. The most important stuff in the universe is nothing. And we don't have the slightest idea why. And that is wonderful. Because if you're a scientist, not knowing is much more exciting than knowing. Because it means there's something else to learn. And it also means, by the way, that the reason I got into cosmology was totally irrelevant. Because matter doesn't matter. The end of the universe is not going to be determined by how much matter there is, but by the nature of the energy of empty space. So, once again, I made a huge mistake trying to solve a problem, but in fact, the problem what nature really told us is much more interesting. And in 1995, I was already driven to realize that most of the energy in empty space, in the universe, was in empty space, although no one believed it. Then the astronomers measured it, and they won the Nobel Prize. Anyway. Now, this means, and I won't go into this, that the universe we live in is probably an accident. And if you want to talk about that, I'm happy to talk about that. But what I want to close with, I want to come back from the universe to something that's maybe more familiar to some of you. I want to talk about the fact that science changes what we mean by good or bad. And I notice there's going to be some talks on quantum computing. Some of you may be developing software literally for quantum computers, or maybe not you, but your children will be. Maybe. And this is a very exciting area of science, potentially, but people are quite concerned about it. What is a quantum computer? It uses the properties of quantum mechanics. Quantum mechanics says, for example, that particles like electrons spin. And we can measure them spinning in one direction or another direction. We call that spin up or spin down. And you could call this a 1 and that a 0. And whoopee, you can make a binary language and build a computer. But the amazing thing about quantum mechanics is that electrons actually spin in many directions at the same time. The strange aspect of the quantum world is that you can measure an electron, and if you measure it, you'll be measuring it spinning in one direction or another. But if you don't measure it, it's spinning in all directions at the same time. It's crazy, but true. Now, if you can exploit that, just think of what you can do. Because if it's spinning in many directions at the same time, then you can do many calculations at the same time. You can make not a bit, but what's called a qubit. And if you could, basically, you can do almost not an infinite number, but a huge number of calculations. If you don't measure the electron, but you manipulate it in ways that use logic circuits, and if the electron's doing many things at the same time, each thing it's doing is doing a different calculation. And you can do parallel computing with a single qubit. And a single qubit would allow you to do things that you could never do with a classical computer. For example, there's a famous problem. Take a large number and find the prime factors of it. That's, of course, the basis of RSA keys, the things that make our world work, the economics of our world. Banks and everyone else use those keys to protect data. You are all probably more familiar with this than me. It works because it would take longer than the age of the universe to try and figure out what the prime factors of a large number are if you didn't know them in your key. It turns out you can calculate it. It would take, if the number has n digits, this is how long in time steps the computer would take to solve the problem. It's what we call a non-polynomial problem in time. But with a quantum computer, an algorithm that a physicist named Shor developed, you could actually, with a quantum computer doing many calculations at the same time, you could make it polynomial. And that means with a quantum computer, you could break the codes of every bank in the world, which is a disaster for your credit cards and your money and your savings. So there's a huge challenge and a huge problem here. But at the same time, there's another side. It turns out that one of the problems you want to know if you're transmitting data is whether anyone has intercepted the data and read it. Now, when I was sending email messages today actually at the hotel with an unprotected network, I wondered how many people were reading those emails at the same time as me. But it turns out that because of something called entanglement, if you take two electrons and very carefully prepare them and move them to the opposite ends of the universe, but if you're a scientist, that's incredibly interesting because it means we may have a whole new way of solving problems, but it also means you'll have to develop the algorithms to do it. The next generation, if quantum computers can be developed, will depend on developing the kind of programming that will exploit that. But almost every job that humans do will be able to be done at some level, ultimately, more efficiently by AI. Now there are huge books being written about the dangers, and you probably know Stephen Hawking talked about it, and my friend Elon Musk worries about it. But I think those worries are misplaced. Because what it'll do is it'll change the human condition. It'll change what it means to be human. But change is not always bad. Let me give you an example to put this in historical perspective. In the 9th century BC, in Greece, writing was introduced. The Phoenician alphabet was introduced. At that time, it was viewed by most philosophers as the end of civilization. Writing. Plato said that written language is an impediment to wisdom because writing never captures the whole truth, and it only gives you the illusion of knowledge. And he said writing would eliminate the need for memory, because if you have something written down, you don't have to remember it anymore, and human memory would go by the wayside. Socrates said written communication will never be as clear as face-to-face communication, because you can't ask questions or argue with a document. They said scholarship and knowledge will end because of writing. Well, that didn't happen. Writing changed the world, but in a better way. A future dominated by artificial intelligence is not necessarily a dystopic future. It can be better, it can be worse. If it is true that machines replace humans, one of two things can happen. Those companies that can control the software development of AI can accumulate most of the wealth of humanity. If that's the case, some small group of people will become rich and everyone else will starve. Or we could use it another way. We could say, this is great. The rest of us can go to coffee shops, listen to music, read books, watch movies, talk to our friends, and machines can do the work if we share the resources and the wealth that's developed by artificial intelligence. The point is, the problem isn't a technological problem. The technology is easy in a sense. The future is not worse, it's different. And whether it's better or worse will depend on us. It's different like the future for books. I think most of us are pretty happy that we can read books now, that the world has changed. It's not worse than it was for Plato or Socrates. It's different. The future way with AI will be different whether we like it or not, but what future we live in will depend on how we use it. And I want to close with this notion, coming back to the relationship between fundamental research and practical research. Too often in the United States and many other countries, governments are interested in funding only research that's applied to solve a certain problem. But as I showed you earlier with the Babbage machine, if we tried to solve the problem of building a better computer with gears and pulleys and didn't fund fundamental research, we wouldn't have computers now. So the example that I want to use comes from particle physics, comes from the person who built the first large particle accelerator in the United States, Robert Wilson. And he was called before Congress and asked if that accelerator would aid in the defense of the nation, because all the United States ever wants to produce is weapons, it seems. And they're governed by that, unfortunately. And what Robert Wilson said, because a particle accelerator won't produce anything useful in that sense. But what he said is, it won't help aid in the defense of the nation. But what it will do is help keep the nation worth defending. And that's the important lesson I want to leave for all of you. Of course you do practical work, but the idea that the ideas you're working on are as important as the products is what I want to stress to you. That what really matters is not how fast our smartphones are, but the quality of the information and the culture and the ideas we develop. And if they don't go hand in hand, then it's not worth developing new technology. Never lose sight of that fact. Thank you very much.